calculate the temperature of Earth, first we need to understand the concept called the solar constant. Okay, we're aiming to find how much energy is available to Earth from the sun and how much heat energy it gives us so that we reach the temperature that we are at right now. To do that, we have to start from the power of the sun, which we know to be that. Intensity is defined as power per unit area. In other words, it's how much energy is incident on unit area per unit time. So to calculate the solar intensity at the location of Earth, we need power of the sun and the surface area that the Earth is located on. So to find how much power per unit area we receive from the sun, we need to divide the power of the sun by the unit area where we are located. So if the sun is here and say Earth is here, and this is Earth-Sun distance. Before we calculate how much power Earth can collect on its surface area, we need to know how much is available per unit area at the Earth's location. So, say this is the surface area of the sphere that the Earth belongs to at a distance d away. The surface area of that sphere would be 4 pi d squared. Imagine Earth as at a point located on a surface area of a sphere with radius d from the sun. When the sun is radiating this much power, once we know how much of that reaches per meter square at the location of Earth, then we can calculate how much of that Earth can collect with its own area. So this calculation, using the value of Earth-Sun distance, gives us about 1,400 watts per meter squared. This is an expression for intensity, and it is what we call the solar constant. It is a measure of power incident per unit area at Earth's distance from the sun. If we have 1,400 watts on each meter squared incident from the sun, and the Earth being a spherical object, how much power is collected by Earth? Now, we're going to model the cross-section of Earth as the collecting face at all times. No matter what time of day, the Earth always has a circular cross-section facing the sun, which would look like that. So if you look at the cross-sectional area of the sphere, it would have an area of the face of a circle, area of a circle being pi r squared. So let's calculate how much power we can collect with this incident power. The power we collect is the power incident on unit area collected by pi r squared area. I'm writing the units in red so you can follow easily. Now, if I calculate that power, this is going to give me how much power in watts that is collected by the circular cross-section of Earth. But this is spread over a whole surface area of the spherical face of Earth. So, carrying on from this much power that the Earth has collected, let's see how much power that means per meter square on the Earth's surface. So we have 1,400 pi r squared watts of power that we have been able to collect. When you divide that by 4 pi r squared meters squared, which is the surface area of the whole Earth, you will see that the pi r squared would cancel and the intensity on unit area on Earth's surface calculates to about 350 watts per meter squared. So once again, 1,400 watts per meter squared is incident from the sun per meter squared at the location of Earth. The Earth collects this power as a circular cross-sectional face of area pi r squared. So multiplying watts per meter squared by the area, we get how much power we can collect, which is here. But that is spread over 4 pi r squared of a spherical surface area. So these terms cancel and we end up with roughly 350 watts per meter squared. This is the intensity on unit area on Earth's surface. So let's remember why we were doing all these calculations. Our goal is to find an average temperature of Earth itself using the energy received from the sun. We found roughly 350 watts per meter squared. Now, how much of this do we actually keep? Unfortunately, we can't keep all of this because some incident energy will be reflected and not contained. So it will not help keep Earth warm. And how much of this is reflected to how much is incident is a term that we call albedo. So albedo is defined as the ratio of reflected energy to incident energy. For Earth, albedo is given by 0.3. That means we keep 70%. So when we say albedo is given by 0.3, that is the ratio of reflected to incident. That means 30% of incident intensity is reflected and not kept. So we're able to keep 70% of what is incident. And now we know how much energy per unit area, per unit time, we actually get to keep. The next step is to use this and the Stefan-Boltzmann law. We're trying to find the maximum temperature we can reach, so we're going to take E to be equal to 1. This sigma is the constant that is given in the data booklet. I omitted the units because I didn't have space. So rearranging and substitution gives this. P over A is the intensity that we get to keep. And this will give temperature as 256 Kelvin, which calculates to negative 17 degrees, roughly, for an average temperature of Earth. Remember, this is a maximum value and a lot of assumptions that have gone into place. But all of this is to show that if we were warming up only by the power incident from the sun, the temperature of Earth today would be maximum negative 17 degrees, which does not allow life to be sustained on the Earth's surface. So why is the Earth warmer? Once again, definition of the albedo is the ratio of power reflected to the power incident on the body. Around 30% is reflected by Earth, so Earth's albedo is 0.3, which means around 70% of incident radiation is what the Earth is able to keep. So why is the Earth not that cold? Before we move on, I'd like to remind you that the albedo depends on several factors such as cloud cover, forest cover, whether there is ice caps, which is high albedo, or ocean cover regions where albedo is low. You should be able to comment on the effect of each of these different factors, different kinds of surface covering in terms of the Earth's albedo. The more reflective, the higher it causes albedo to be. For example, ice caps cause albedo to be high because they reflect more, whereas ocean cover regions have albedo low because they absorb more. Now the next concept we're going to talk about is greenhouse gases. So various gases in the atmosphere can absorb radiation at infrared region. Now the concept of resonance means oscillating at the same frequency, and certain gases in the atmosphere, which are carbon dioxide, methane, water, and N2O are called greenhouse gases. And these are the gases that are able to resonate with infrared radiation, meaning they can absorb the energy from infrared and re-emit it back to Earth before heat leaves the Earth. Let's see how this works. Okay, so this simulation is going to show us a methane molecule receiving infrared photons. You know, different regions of the electromagnetic spectrum have different frequencies. So this molecule can resonate with infrared frequency. That means, just like carbon dioxide we're looking at now, they can oscillate at the same frequency as infrared photons, which allows them to absorb the energy and emit it again. With visible photons, it doesn't happen because the frequency is different, so they only resonate with infrared. When I change the molecule to water and the photons back to infrared, I see a similar pattern taking place. Now, let's see what this means in terms of the temperature of Earth and the composition of the atmosphere. If I look at this simulation, this shows no greenhouse gases in the atmosphere, and all of the infrared photons incident are reflected off the Earth's surface. When I change parameters to ice age values, you see that some of the infrared photons are reflected and contained inside the atmosphere. So when I change to today's values, I can see that more of the infrared photons are contained and the average temperature is shown to be higher. So the more greenhouse gases in the atmosphere, the more infrared photons are re-emitted back to Earth, and that increases the average temperature of Earth. This is called the greenhouse effect. Finally, let's see what happens when I increase it completely on this simulation. You'll see that more of the infrared photons are sent back to Earth and the temperature rises. So as you can see, it's not a simple mechanism. It's actually a very complex mechanism, but we owe it to greenhouse effect that we have a temperature higher than negative 17 degrees Celsius. We have the atmosphere as a blanket on the surface of Earth due to the greenhouse gases. So let's talk about balance. To maintain balance on Earth, we need a balance between energy and energy out, and we want that temperature to be maintained. Normally, we owe this to greenhouse effect. However, increasing the amount of greenhouse gases in the atmosphere causes an increase in the temperature. And most scientists believe that producing more of the gases absorbing infrared radiation is due to human behavior, which upsets the balance, and this is called the enhanced greenhouse effect.
Two final terms regarding energy and efficiency are energy density and Sankey diagrams. Energy density is the amount of energy per unit volume available from a fuel. Its SI unit is joule per cubic meter. This is a term that we use to compare various fuels and their energy output. Sankey diagrams are tools to represent the energy transformations that take place in a system. Two examples are seen here. The LED bulb is 75% efficient, so the 25% thermal energy produced is shown with an arrow downward on the diagram. The diagram for the filament bulb is 20% efficient, shown with the straight arrow, and the wasted energy is shown with its respective arrow downwards. Observe that in Sankey diagrams, the width of arrows represent the size of the amount of the energy they represent.